Hey everybody, my name is Kelvin and welcome back to my channel. Today, we're going to be talking about bounding boxes in computer vision. Most people first learn computer vision through image classification. That makes sense because image classification is the easiest version of the problem to understand. We simply give a model an image and the image predicts a label. For example, your model might look at an image and say, it's a dog or a cat or a bird. That's useful, but real images are usually more complicated than that. If an image has a dog, a person, a chair, and a car, one label is often not enough. We don't only want to know that something exists somewhere in the image, we want to know what each object is and where each object is located. That's the jump from simple image classification to object detection. Object detection combines two tasks, that being classification and localization. The classification part answers what exactly is the object, while the localization part answers the question of where is the object. A bounding box is a rectangle around an object. In the photo I have here of our complete model, we see bounding boxes across all three people. The common format for a bounding box is xmin, ymin, xmax, and ymax. These four numbers describe the rectangle. Xmin describes the left side of the box, Ymin is equal to the top side of the box, Xmax is the right side of the box, and Ymax is equal to the bottom side of the box. Instead of a model simply saying dog, an object detection model can say the label is a dog, the box is Xmin, Ymin, Xmax, Ymax, with some confidence attribute. That's much more useful. That is the kind of output behind systems that detect pedestrians, faces, products, vehicles, medical abnormalities, and objects in security footage. In this video, we're going to be working on training an object detection model like this. Specifically, we're going to fine-tune a faster RCNN model on the Pascal VOC dataset. Before we start, it's important to understand what fine-tuning means. We're not just going to make the model learn visual understanding completely from random weights. Object detection is a harder problem than simple classification because the model has to learn both what objects look like and where they are located in the image. It needs to learn object categories, object boundaries, candidate regions, and bounding box adjustments, and that takes a lot of data, training time, and computing power that I don't have. So, instead, we're going to be using a pre-trained backbone. A pre-trained backbone is a feature extractor that has already learned useful visual patterns from a large image dataset, hence it being pre-trained. It has already learned low-level and mid-level image features such as edges, textures, curves, corners, and object-like shapes. And what we're going to do is to attach a detection head that will learn the specific classes and bounding boxes for our specific dataset. Training from scratch means teaching the model vision from ground zero. Fine-tuning is we're going to start with useful visual features and then we adapt them to our task. And that's the practical approach we're going to be using here. In the end of this notebook, the model should be able to take an image and output predictions in the form of predicted label, a confidence score, and some predicted bounding box. And obviously, the results will not be perfect, and that is okay. A model like this needs a lot more training and fine-tuning to make production ready. Here, I'm just going to be going over the workflow, preparing an object detection dataset, training a detector, comparing predictions to ground truth, and understanding what the model is getting right and wrong. Before we jump into the code, I have something I'd like to share with you. If you've been enjoying the content on this channel and want to support what I'm building here, check out my book Modern Data, From Ingestion to Production. It's a practical introduction to how data moves through modern systems, from ingestion and transformation all the way to production use. It's available on Amazon, Barnes & Nobles, and Apple Books, and the ebook is only $6, so it's a really affordable way to support the channel and learn something useful at the same time. Be sure to check out the links in the description. Let's jump into the code now. Here, the first code block will import everything we need for our notebook. At a high level, this block prepares our tools. We need tools for loading data, training the model, visualizing any images, drawing bounding boxes, and tracking our training progress. This package torch here is the main PyTorch library, which gives us tensors, model training tools, gradient calculation, optimizer, and device management. From Torch Utils data, we import dataset, data loader, and subset. Dataset here lets us create a custom dataset wrapper. Data loader feeds batches of data into the model during training, while subset lets us use only part of the dataset. In this notebook, we use half the dataset, so training is a bit more manageable for my side. And then specifically here, matplotlib.patches is going to help us actually draw the bounding boxes. Here we're going to be using PIL images because the dataset gives us images as PIL images before we convert them into tensors. The VOC detection here is the dataset class from Torch Vision that will help us load our dataset. This line right here will give us image transformation functions. We're going to be using f.toTensor to convert PIL images into PyTorch sensors. Then we'll import the faster RCNN model, like this. Faster CNN ResNet 50 gives us object detection architecture. Fast RCNN predictor lets us replace the final prediction layer so it outputs the correct number of classes for Pascal VOC. Then ResNet 50 weights is going to help us initialize the backbone with pre-trained visual features. Let's run this and get our library set up. The next block here will help us choose where our model will run. In my run, I'm going to be using the CPU. This matters because object detection models are heavier than basic image classifiers. Training on CPU is slower, so we should not expect this to train as quickly as it would on a dedicated GPU. Here, my device will be using CPU, so the load times may vary depending on the power of your machine. Let's run this, and we can verify that we are running on our CPU. Then, we're going to define the Pascal VOC classes. This block specifically defines the class labels for the dataset. At a high level, this code creates the translation system between human-readable labels and numeric labels that the model can understand. Pascal VOC has 20 object classes, including person, dog, car, cat, chair, bus, train, TV monitor. We're also going to be including an extra class, background. Object detection models usually need a background class because not every region in an image contains an object we care about. So the total number of classes here will be 20 object classes and a background class. As we mentioned, the model can't train directly on string labels like dog or car. It needs numeric class IDs, which we're going to create using this code. This will map class names to numbers. We can run this, and we can see that now our classes are mapped to specific integers. For example, dog is 12, potted plant is 16, and bottle is 5. And here, IDX to class will actually help us do the opposite now. This will help us convert numeric predictions back to readable labels. Here, num classes will store the total number of classes. Then, let's actually load the dataset. At a high level here, we're using Torch Vision to get real object detection dataset that already contains images, object labels, and bounding box annotations. The helper function, load raw VOC dataset, will take two main arguments. The root argument tells Torch Vision where to store or look for dataset files. In this notebook, the folder is ./data. The image set argument tells Torch Vision which split to load. We're going to be using two splits, training and validation. The training split here is going to be used to actually update and train the model, while the validation split is used to test the model on images that it did not train on. I've already taken the liberty of running this code, so we can just verify that we have the data that we need, and we can also examine how many images are in each set. In our train data set, we have 5,717 pictures, while the raw validation has 5,823. Each item in this dataset will contain an image and a target. The image here is the actual image, while the target is a nested annotation dictionary which contains metadata, labels, and information for bounding boxes. This block gives us access to real object detection examples. Let's inspect a raw example. The block here will inspect one raw dataset example. We're going to be checking what the dataset actually gives us before we start converting it to the model. We load the first training example. Sample image, sample target. We can run this, and in this run, we see that the type of the image is pil.image.image. while the target type is a class dictionary, and the image size is 500 pixels by 442. For PIL images, this means that the width is equal to 500 and the height is equal to 442. The code here also will take a look at the annotation keys. The output of this line of code here, this annotation keys, will show us keys like folder, file name, source, size, file, segmented, object, while the key that we care most about here is object, which is where the object labels are and the bounding boxes are stored. In this first example here, the object annotation showed two objects, a horse and a person. We can confirm this down here, name horse, and we can also see an object with the name person. And it makes sense because we can see a person and a horse within this image. The idea behind this is that the model will have to learn that there is a horse in a particular region and that there is a person in a particular region. The purpose of this is to show the raw annotation structure that we need to convert. Our next block of code here, at a high level, will create is a function that converts raw VOC annotations into the target format faster RCNN expects. This function takes the nested annotation dictionary and turns it into clean PyTorch tensors. The raw VOC annotation stores object information in a way that is easy to inspect, but the model needs a specific structure. Faster RCNN expects each training target to include fields like boxes, labels, area, and is crowd. The boxes field will contain bounding boxes. Again, remember that each box will use xmin, ymin, xmax, and ymax. The labels field will contain numeric class IDs. The area field contains the area of each bounding box, and the isCrowd field tells the model whether the object is part of a crowd. In this tutorial, we're going to just give every object a 0. The code will retrieve the object annotation. Then we handle the special case of if is instance objects dict. This is necessary because VOC stores a single object as a dictionary, but multiple objects as a list. We want to loop through objects consistently, so we convert a single object into a list with one item. In the loop, we're going to get the class name, then convert it into a numeric label. Then, we'll read the bounding box values. The coordinates are converted to floats and stored in the box's list. After the loop, we convert the Python list into PyTorch tensors. Let's run this code. And now we've defined our function. In the next code block, I'm going to create a custom dataset wrapper. This block here will help us create a custom PyTorch dataset wrapper. This class makes the raw Pascal VOC dataset compatible with the faster RCNN trading loop. Again, the raw dataset gives us a PIL image and the annotation dictionary, but the model will require an image tensor and a target dictionary with tensor boxes and labels. So this wrapper here will do that conversion for us automatically whenever we access an item. From this point on, when we load an example from VOC dataset for detection, we already know that it'll return the format the model needs. Let's run this and get that ready. This block here will create the training and validation datasets that we'll actually use. We're going to be taking the full converted dataset and using only half of it. Remember that the full training dataset has 5,717 images, while the notebook here will use half of that, which is 2,858. The full validation set from before was 5,823, while we're only going to be using 2,911 validation images, which is a practical compromise. Object detection models, as mentioned before, takes longer to train than just simple classifiers, especially on a CPU like mine. Training on a very small subset would be much faster, but the results would probably be weak. Training on the full dataset would give the model more examples, but it would take much longer. Using half the dataset gives us thousands of images while keeping the notebook manageable. Next, we're going to be creating the data loaders. The block here creates data loaders for training and validation. Data loaders are responsible for feeding data into the model in batches. Our ColeFN is custom. For image classification, batching is usually simple because each image has one label, but in object detection, it's different because each image can have a different number of objects. Because of that, we cannot simply stack all targets into one fixed size tensor. Our custom collate FN keeps the images and targets as lists, which matches what torch vision detection models expect. Here, the training data loader will use batch size equal to 2 and shuffle set to true. A batch size of 2 is small, but object detection models use more memory than simple classifiers. It's a simple choice for CPU training. The shuffle is equal to true means the training examples are mixed each epoch, which helps training. In our validation, we're only going to be using a batch size of 1 and a shuffle false. Validation does not need shuffling here. Let's run this first and initialize our data loaders. For our next code block, this block here will visualize a training example with its ground truth boxes. At a high level, the code checks that our converted dataset is correct before we start training. The draw target boxes function takes an image tensor and a target dictionary. An image tensor has shape, channels, height, and width. Matplotlib expects height, width, and channels. So we're going to be using image tensor.permute 1, 2, and 0. This helps us rearrange the dimensions. Then we draw the image. After that, we loop through the target boxes and labels. Each box is stored as an xmin, ymin, xmax, and ymax. To draw it with Matplotlib, we need to calculate the width and the height. And we can find that by doing xmax minus xmin, and height is equal to ymax minus ymin. And this will store width and height for Matplotlib. Then after that, we're going to be creating a rectangle and adding it to the plot. And then from before, we're going to be using our IDX to class here to convert the class ID into a readable label. We've made it so that our boxes are set in blue. This will help us differentiate from our ground truth boxes, while we're going to be using red for our model training predictions. Let's run this, and we can see here that we've added our bounding boxes here. We see a person from before in the box that it should be in, and the horse within the box that it's supposed to be in. The next block here serves to create our faster RCNN model. We're creating an object detection model and modifying its final prediction layer so it matches the number of classes in Pascal VOC. The model here will use ResNet50 as a backbone. The backbone is the part of the model that extracts visual features from the image. Here we use weights backbone is equal to ResNet50 weights.default, which means the backbone starts with pre-trained visual features, while the model itself is created with weights is equal to none. We're not using a fully pre-trained detector. We are using a pre-trained backbone and training the detection components for our specific task. Then we get the number of input features going into the final classifier. After that, we replace the final prediction layer. This is necessary because the final layer needs to output predictions for our 21 classes. The final predictor is responsible for predicting object classes and bounding box adjustments, and because this final predictor is newly created, it has to learn during training. That explains why results may be imperfect after only a few epochs. The backbone starts with useful visual features, sure, but the detection head still needs to learn how to map those features to our specific objects and boxes. Our next task here is just to set up the optimizer and scheduler. At a high level, the optimizer controls how the model updates its weights during training. First, we collect all model parameters that require gradients. Then, we create an SGD optimizer with a learning rate of 0.005. The learning rate controls the size of the model's weight updates. The momentum is set to 0.9. Momentum here helps smooth out the updates and can make training more stable. The weight decay here is 0.0005. Weight decay is a regularization technique. It adds a small penalty to discourage overly large weights. Then, we'll create a learning rate scheduler called LR Scheduler. Here, we lower the learning rate every 2 epochs by multiplying it by 0.1, which means the training starts with larger updates, then later uses smaller updates. This helps the model to make faster progress early and more careful updates later. This block sets up the mechanism that will update the model weights during training. Let's initialize this. In our next code block, we've defined a function that will help us train for 1 epoch. This function will loop through the training data once, calculate the model's losses, update the model weights, and return the average loss. Inside the loop, every batch gives us images and targets. The images are moved to the selected device using this. The targets are dictionaries, so we move every tensor inside each target dictionary to the device as well. Then, we're going to be calling lossDict is equal to model images and targets. During training, FasterRCNN returns losses instead of predictions. This is because we provide both the images and the correct target boxes and labels. The image here can compare its internal predictions to the target and calculate how wrong it is. The loss dictionary here can contain multiple components such as classification loss, box regression loss, objectness loss, and region proposal loss. We combine these into one total loss. Then we perform the standard PyTorch training steps. Zero grade here will clear old gradients, losses backward calculates new gradients, and optimizer.step will update the model weights. At the end, we're also going to be calculating the average loss. This will give us one average loss value for the full epoch, and this block here is the core of the training process. Let's initialize this. Our next step here is to actually run the training. Here, I've set it up so we've trained the model for 5 passes through the training dataset. Here, we're going to be storing the average losses in our training losses variable. Inside the loop, we call train1epoch, which trains the model for one epoch and returns the average loss. Then we call our LR scheduler. Then we're going to be appending our average loss to our list and print it. I've already ran this model, and this took over 5 hours. So you can kind of see why I decided to only use half the dataset. I've already trained this, so we don't have to wait this long again, but if you're running this on your own machine, beware that this may be a long process. In my run, the average training losses were approximately epoch 1 is equal to 0.57, epoch 2 is equal to 0.50, epoch 3 is 0.41, epoch 4, 0.38, and epoch 5, 0.36. The loss consistently decreased from around 0.57 to 0.36, which tells us the training loop is working. The model is receiving images and targets, calculating losses, and updating weights in a useful direction. While the loss goes down means that it's improving, it doesn't mean the model is yet perfect. It means the model is improving according to its training objective. For object detection, we still need to inspect predictions visually, because a lower training loss does not automatically guarantee perfect boxes or perfect labels. Here, I've set it up so we can plot our training loss. You can see the results. Start at 0.57, and we go down to 0.37, or 0.36. Here, the training setup appears healthy. This code here will just simply save our trained model, which I've already done, so I don't need to do this again. But if you want to keep it, this is what the file will look like. Our next goal here is to actually create the prediction function. This block defines the inference function. This function takes a trained model and an image tensor, runs object detection, filters predictions by confidence, and then returns readable results. We first switch the model to evaluation mode, using model.eval. Then we use with torch no gradient, which tells PyTorch not to track gradients because we're not training during inference. The model expects a list of image tensors, so we call model image tensors to device. Even though we're predicting on one image, we still pass it inside as a list, and the model here returns a prediction dictionary with boxes, labels, and scores. The boxes here are predicted bounding boxes, the labels are numeric class IDs, the scores are confidence scores. Then we move those tensors to the CPU and detach them from PyTorch's computation graph. After that, we're going to be looping through every predicted box, label, and score. Pay attention to this if score value is less than confidence threshold. If a prediction has a score below the threshold, we skip it. For predictions that pass the threshold, we convert the numeric label into a readable class name using our IDX to class. Here we can set our confidence threshold, so we'll take a look at that later. Our next code here is to draw the actual model predictions. The block here defines a function that visualizes the model's predictions. It draws red bounding boxes on top of an image and labels each box with the predicted class and confidence score. Specifically here, we're going to be converting the image tensor from channels, height, and width into height, width, and channels using image tensor permute. And then it'll display the image. After that, it loops through the predictions, the bounding boxes, and then it loops through the predictions. Using this information, we'll create a red rectangle and add it to the plot. And we'll also return label text like chair, 0.90, person, 0.73, and sofa, 0.61. Run this and get this ready. Our next code block here will test the trained model on one validation image. We're going to be comparing the dataset's ground truth boxes with the model's predicted boxes. We get one validation example and then we run inference. We're going to be using a confidence threshold of 0.5, which means we only keep predictions with at least 50% confidence. The first visualization will show the ground truth training boxes in blue, while the second visualization will show the model's predicted boxes in red. Let's take a look at this. This is our training. You can see that the TV monitor from the ground truth example is correct. This is a TV. And then we jump down here. We see that our model has predicted that this is a TV monitor with a confidence 0.67, which brings it over the 50% confidence threshold. In the backend, this tells us that the model predicted class is equal to TV monitor, confidence is equal to 0.67, and the box coordinates are 26, 2, 483, 288. And these numbers here correspond with our x min, y max, etc. And that's our complete object detection prediction. Our model here has successfully learned that this is a TV monitor. The predicted box is also in the correct general region, and it covers the monitor area. However, the predicted red box is noticeably larger than the ground truth box. It extends farther to the right and covers more of the surrounding image. This tells us the model understands the object location generally, but its localization is not tight as the ground truth. And that's pretty common object detection behavior. A model can get the class right while still producing a loose bounding box. Our confidence score of 0.67 also makes sense. The model is not really just saying that the prediction is extremely certain, but it is confident enough to pass our 50% threshold. Let's test on another few random images. We basically do what we did before, but just randomly. On this, see that there's a bird here. I also set the confidence threshold to 0.75. So this will filter out more predictions. Let's run this and examine our results. We can see that there's 2 people or 3 people here. And we see that our model has successfully detected that there are people in this image. We see that this prediction right here is very close to what it should be. But if we hop down here we see that there are multiple person boxes here. Some boxes are very close to each other, and some may represent the same object more than once, which is what it's doing here. It means that the model is finding object-like regions, but it's not really perfectly separating every object yet. This tells us that the model is really learning, but the detector still needs more refinement. The image shows that object detection quality isn't just about whether a box appears on the image. We have to look at, are the predicted classes plausible? Are the boxes in the right regions? Are there any duplicate boxes? Are similar classes being confused? Are the confidence scores reasonable? The model here is working, but there is much room to improve. Our next code block here is we're going to try different confidence thresholds. This block tests how the confidence threshold changes the model's output. The code will loop through our 4 thresholds, 0.2, 0.4, 0.6, and 0.8. For each threshold, it runs the prediction again and counts how many detections remain. At 0.2, we see that the model keeps many predictions, while it includes useful detections but also weaker and noisier ones. At 0.4, we see that it's mostly filtered out the noisy ones. We have 4 here and 4 here. But at confidence threshold 0.8, we see 3 bounding box person objects, which matches our ground truth from up here. Let's try this image with a confidence threshold of 0.8. We can borrow our code up here for this. Confidence threshold equal to 0.8, while the index was 550 in the dataset. Run this. And now we see that our object has successfully detected that there's a person here person here, and a person here, which aligns with what we're seeing in the ground truth image. I've also built a couple of tests here, which add basic tests for the target and prediction structures. At a high level, these tests check whether our data is well formed. They aren't really designed to measure models' accuracy. First test, as target format, checks that the validation target has boxes and labels. It also checks that the boxes are a 2D tensor, and that each box has 4 values. Remember, this matters because our rebounding box should have an x min, a y min, an x max, and a y max. The second test here, test prediction format, checks that every clean prediction has a label, score, and box. The third test here is test boxes inside image, which check that predicted boxes stay within the image boundaries. We can run this and we can see all 3 of our tests passed, which means our targets and predictions are structurally valid. In our next block here, we should also inspect the raw model output before we filter predictions by confidence threshold. When we can see the raw output here. At this point, we've seen the entire object detection pipeline in action. Object detection is where computer vision starts to feel much closer to real-world practical uses. A classifier can tell us what is in an image, while the object detector can point. While an object detector can tell us where the things are within the image, and that matters. A model can predict both a class label and a bounding box. Once a model can predict both a class label and bounding box, it can start doing a lot more practical work to count things like objects, track objects, detect people, vehicles, products, or any other system that make decisions based on what appears in an image or scene. And the core output here is simple: a label, a box, and confidence scores. In this notebook, we trained a real object detection model to produce those outputs. Sure, the results were not perfect, and that's important. Real machine learning does not always produce flawless predictions immediately. The model improves as we give it more data, more training time, better hardware, and better evaluation. But this is the bare bones foundation. From here, there are a couple ways that we can continue improving the model. We can train for more epochs. We can use the full dataset. We can speed up time by using a GPU. We can also randomize the subset selection, tune the confidence threshold, compare ground truth and predictions a bit more formally, try different model architectures, and train on a custom dataset. And that's it for this video. Thanks for watching, Don't forget to like and subscribe, and I'll see you guys in the next video.